Hello, and today we're doing the Izod Impact Tester. I'm Derek.
I'm Izod.
I'm Eric.
I'm Sabrina. The purpose of this lab was to test the strength of 3 materials: steel, brass, and aluminum. All these samples are the same size, however, the notch on the steel is slightly bigger. This is because it has the ability to absorb more energy. It would be the strongest material. The objective of this experiment requires us to learn how to use the Izod Impact Tester, as well as determine which of the samples is the strongest. Our theory for this experiment is that the material that requires the most force is the strongest, and the material that requires the least amount of force will be the weakest. We will be using several formulas to calculate the following of our 3 samples, which include initial and final potential energy, amount of kinetic energy required to break the sample, difference in initial height, and impact velocity. Using these formulas, we can determine how much kinetic energy was used to fracture the sample, the differences in initial and final height and potential energies, impact velocities and strengths.
Alright, so for the procedure, basically you start by pulling the pendulum towards the right, just enough so it can get locked up into the block. And after, you take the piece of metal and put the longer side inside the thing so it's more sturdier. And after you lock it up, make sure it's sturdy, pull the pendulum all the way back, and then you have to hold the latch bar in the up position by pushing down on the handle and place it in the latch position. Bring it back down, make sure it's gonna hit this metal in the right spot. After, raise the pendulum by hand all the way until it stays, so you'll hear a clicking noise and just leave it there. You have to put the stop pin in number 2, shut the safety gate. After that, pull on to the lever so it lets go of the pendulum and watch it dent the metal or possibly break it. Then after, insert the stop pin into the first hole, so it's from the right, and then ensure that there's no accidental release into the pendulum. Set the pointer, measure the angle of it, and record your observation. Then after, put it back, pull out your piece of metal. It'll end up looking like this after, or worse, but this is steel, so this came out to be our strongest. And after that, once the pendulum is complete, remove the pin and put it back. Read and record there. Alright, so today we're testing out the strength of steel with the Izod Impact Tester. First, gonna move the latch. Lock it up. And the longer side goes inside the impact tester. Do this amazing device now. Tighten it up. Okay. Alright. And then just pull it backward. Alright, that's perfect. Yeah, make sure that's at 0 there.
When you hold the pendulum, you should hold like this, all the way from your thighs, not from
What's going to happen now is he's releasing the lever, which is going to let the hammer fall, bring the potential energy into kinetic energy, which is going to impact the sample.
That basically went snapped in half. And it's done. Alright, so as you can see, metal's a little bent, you can't see, so just once. what happened with that was it went and got snapped in half, and as you can see, come up. So that basically, yeah, that was it.
We're using this scale because it's the best way to hammer on right now. So we're looking in orange, and this is the amount of energy required to break the sample.
Yeah, so that was 40, roughly about 35 foot-pounds. Alright,
And now we have to measure the angle.
so the angle of this. Okay. The angle of this.
No, you may. This is the reason.
That's approximately 40 degrees up from the starting point. So you can see that it didn't completely break off. So steel tends to be really strong. And that's why.
Hello, and in this experiment we had several calculations we need to do after the testing to figure out potential energy, check for free radical values, and everything like that. The following equations on the board are equations we used in this lab to figure out unknown and known variables. First equation was for potential energy, which is equal to the mass, which is 12.0 kilograms, times gravitational constant, 9.81, times by initial height of A, which was equal to 573 milliliters. The height after impact, which was figured out through the radius, times by 1 minus cos beta. Beta was the angle at which we measured the pendulum swinging past after impact. After finding all this data, we used it to figure out the overall energy to break the sample, which was energy which is equal to work. Work is equal to mass times gravitational constant, times by the height before impact, multiplied by the height after impact. Subtracted from each other. After this, we took those initial values and used them to figure out percent error. Percent error was theoretical minus calculate over theoretical, and over calculate. Theoretical value was the value we read on the gauge itself. In the data from this experiment showed that steel was the strongest, aluminum was the middle, and brass was the weakest. The theoretical value for how much energy required to break steel was 54.35 joules. The amount of energy required to break aluminum was 26.5 joules. And the amount of energy required to break brass was surprisingly only 7.82 joules. That was theoretical. The actual values measured were 55.12, which gave a percent error of 1.4%. 25.76 joules, which gave an error of 1.11%, and 8.46, which gave a percent error of 8.18%. Izod value was 776.4 kilojoules per meter squared for steel. For aluminum, 325.6 kilojoules per meter squared, and for brass, 97.75 kilojoules per meter squared. And the ASTM value was 7,764 joules per meter. Brass, 997.5 joules per meter. And for aluminum, 3,256 joules per meter.
The Izod Impact Test is a strength test that determines the force required to break any material. This is conducted with a weight placed on the end of an arm, and the device swings the pendulum in motion. Once it hits the sample, the dial will show you just how much energy is required to break the material. The angle that is recorded is used in a series of calculations to figure out other measurements to compare between the samples, such as the difference in height and impact velocity. The three samples we used were steel, brass, and aluminum. Our hypothesis was that the steel would be the strongest, brass would be the second strongest, and aluminum would be the weakest. We thought the denser materials would be stronger, and our original hypothesis was wrong. The aluminum proved to be stronger than the brass. The aluminum sample would require triple the amount of energy that was required to fracture the brass. The experiment has demonstrated that the density and the weight are not the only factors to consider when determining the energy required to break a sample. The brass sample broke with less energy and is relatively brittle compared to aluminum. Brass was struck with the weight, it was enough energy that it broke in half. Aluminum was more elastic and was able to absorb more energy compared to the brass. Its yield point is less than brass, but after that point, it can still absorb more energy than the brass could. One source of error that occurred during the experiment is that the rotating hammer produced friction in two ways. By rotating on a shaft and from the air that it passes on the way down to reach the sample. Another possible error was misreading of the values and the angles. The final result is that steel was the strongest and also the heaviest. Aluminum was the lightest and the second strongest. Brass was just the weakest. Engineers can use all these different properties to apply these different materials to different uses. Aluminum is not the strongest steel, but it is able to withstand light and repetitive forces. This information is very useful, and all materials can be used in their own unique way for the greatest efficiency. Copper does not have great structural properties, but it is a great thermal and electrical conductor. It's best suited for wiring and thermal elements.
For this investigation, we tested the strength of copper, aluminum, and steel through the Izod Impact Test. We hypothesized that steel would be the strongest, brass the average strength, and aluminum as the weakest.
Our results determined that the steel was the toughest, and to our surprise, aluminum was the second strongest, and the weakest was brass. We understood why brass was the weakest as we learned brass was more brittle and aluminum had more elasticity.
We also learned that steel is well suited to withstand greater forces, while aluminum is better withstanding constant small forces.
Our results were somewhat unexpected. However, it taught us a valuable lesson that it is difficult to tell how the material will react without actually testing it and the strength. And that's the end.